So for this problem, we have a piecewise defined function. And I'm going to show you not just how to do this problem, but how to do other problems that are like this that might show up. A lot of times people want to learn how to work the particular problem on their practice test or their homework without realizing that they need to make sure that they know all of the concepts a little more in depth to be able to answer the question correctly. So this one says, sketch the graph of the function and find the x values at which f is continuous but not differentiable. Other ways that this question could be asked is you might have something where it has an a in one of these, and it will say, find the value that makes the function continuous. Or it might ask for at what points is it discontinuous and why. There are lots of different things you could do here. But the first thing that you have to be able to do is to know how to graph it. And so I want to make sure that you know the different families of graphs. So let's just make sure that we know that. So families of functions. So the first one are constants. So those are just horizontal lines. So if I have the graph f of x equals 5, that's just the horizontal line at 5. So that is the first one, so you need to make sure you know how to graph constants. The second one are linear. So linear means it has an x to the first power. It's linear, not counting constants. So anything that looks like this, 1/2 x, x over 3, 3x plus 2, minus x plus 7, those are all linear. And since they're linear, you know they're lines. That means you only need to know 2 points to be able to graph the line. 2 points determine the line. So if I had f of x equals 3 for x less than or equal to 1, and 5x minus 2 for x greater than 1, and I needed to graph that, then I know that 3 is just a constant, so it's a horizontal line. It's less than or equal to 1, and so that means I put a solid dot there. For this one, it's 5x minus 2 for x greater than 1. I only need to, it's a line because it's x to the first power. I only need 2 points to graph that line. One of these points is going to be 1. So I'll plug in 1, and I get 5 times 1 minus 2, and that's 3. That point I already have, so that's a point that's on there. And now I'll just plug in any other point. I'll plug in, now I need to be something greater than 1, so maybe I'll plug in 2. So 5 times 2 minus 2, 10 minus 2 is 8. So at 2 I have 8. 4, 5, 6, 7, 8. That's another point on my graph, and it goes like that. So that is how you would graph this one. Now, those two, that makes this graph continuous because they meet up at a point. If I had f of x equals 2 for x less than 0 and 4x minus 1 for x greater than or equal to 0, then here I'll go to x equals 0, and I have, it's 2 on the left side. Now I put an open circle because it does not include the equal sign. And then 4x minus 1 at 0, that would give me 4 times 0 minus 1 is negative 1. It does include the equal sign, so I put a solid dot. I need to put another point in there. I'll use 1. At 1, it's 4 times 1 minus 1, that's 3. Right there. So that would be this one. And then just one more example. Let's say I had f of x equals 3x, negative 3x plus 1 for x less than negative 1, and 2x for x greater than or equal to negative 1. Okay, so these are both lines. Notice this line has a negative slope because the coefficient of x is negative. A negative slope means it's going to be sloping downward. This one has a positive slope, so it'll be sloping upward. So x less than negative 1. So I'll plug in negative 1, negative 3 times negative 1 plus 1, that's 3 plus 1 is 4. So at negative 1, it's 4, but that has an open circle because it does not include an equal sign. I need to get one more point, so I'll put in negative 2. It needs to be less than negative 1. And that'll be negative 3 times negative 2 plus 1. That's 6 plus 1 is 7. So at negative 2, it's 7. So it's 4, 5, 6, 7. Right there. And so it goes like that, and it stops at the open circle. And then for 2x, x greater than negative 1. So I'll plug in negative 1, and I get negative 2. And that's a closed circle because it includes it. And then I'll plug in, whoops, that was at negative 1. Should have been right there. And then I need one more point. And so I'll plug in 1, and at 1 it's equal to 2. And so my line looks like this. Now, if I were asked if these graphs were continuous or not, I would say this one's continuous. And the reason why it's continuous is 3 is continuous, and 5x minus 2 is continuous. And so the only point we have to check is where they meet up. And I would say the limit as x approaches 1 from the left of f of x equals 3. The limit as x approaches 1 from the right of f of x equals 3. So the limit of f of x as x approaches 1 equals 3. And f of 1 equals 3. And these things together make it continuous. So to make something continuous, you have to show that the limit at a particular point, the limit as x approaches a of f of x exists, and that it equals f of a. If I get a chance, I'll try to remember to show you one where that's not true. And so this one is continuous, continuous on negative infinity to 0, union 0 to infinity, but not continuous, discontinuous at 0. And the reason why is the limit as x approaches 0 from the left of f of x is 2, and the limit as x approaches 0 from the right of f of x is 7. And so the limit does not exist. So the limit as x approaches 0 of f of x does not exist, and a function cannot be continuous if the limit does not exist. The same is going to be true for this one. And what did I just say? I was going to try to remember to show you. Oh yes. So let's say I had f of x equals 2 for x less than 1 and 3x minus 1 for x greater than 1 and 4 for x equals 1. So x less than 1, it equals 2. For x greater than 1, it's 3x minus 1. So I'll plug in 1, and when I plug in 1, I get 3 minus 1 is 2, but it's an open circle because there's no equal sign. It's a line, so I need one more point. I'll plug in 2, and I plug in 2, I get 6 minus 1 is 5. So it's like that. And then I have this last bit, at x equals 1, the value of the function is 4. So I put a solid dot right there. So this is discontinuous. Discontinuous at x equals 1 because the limit as x approaches 1 of f of x equals 2, but f of 1 equals 4, and so the limit as x approaches 1 of f of x does not equal f of 1, and whenever that happens, it is discontinuous. Okay, before I go on with my discussion of the different families of functions, I want to look at another way this question about continuity might be asked. So let's say that we had a function that looked like this. So this is our function, and the question was, what value of a makes this function continuous at x equals 1. And so to be continuous at x equals 1, the limit as x approaches 1 from the right of f of x has to equal the limit as x approaches 1 from the left of f of x, and the limit as x approaches 1 of f of x has to equal f of 1. This second part's not going to be a problem with this function because less than or equal to 1 has the equal to it, so the whatever limit we have as it approaches 1 from the left is what it's going to actually equal at 1. And so the limit, what you do for these is I say the limit as x approaches 1 from the left, and I take the value of the function to the left of 1, which is 2x plus a. So the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the left of 2x plus a. And then what is that limit? Well, I'll plug in 1 for x, and I get 2 plus a. Now I need to take the limit as x approaches 1 from the right of f of x, and that will equal the limit as x approaches 1 from the right of x squared plus 2, and that equals 1 plus 2, which equals 3. And now in order for this thing to be continuous, these two limits have to be equal. So 2 plus a has to equal 3, or a has to equal 1. And so if a equals 1, then the limit as x approaches 1 from the left of f of x equals 2 plus 1, which is 3. The limit as x approaches 1 from the right of f of x equals 3. The limit as x approaches 1 of f of x is 3. If the right and left hand limits are equal, then that's what the limit equals. And f of 1 equals 3, because if we make a equal to 1, then so if a is 1, this is 2x plus 1, and when x equals 1, you'd plug into that and you would get 3. Okay, now back to my original goal over here was to talk about families of functions. We did constants. We've done lines. And then the next you'll have our quadratics. And anything that has a quadratic term, that just means it has an x squared term. It's going to be a parabola. It'll look like that, or it'll look like that. And it'll look like this if the x squared term is positive, and it'll look like this if the x squared term is negative. I'm not going to go into a lot about how you find the vertex and everything, but I do want to remind you a little bit about the basics of translation. So our parent function is x squared, y equals x squared. That has the point 0, 0, and the point 1, 1, and the point negative 1, 1. And then if I make negative x squared, that flips it upside down. So negative turns it that way. And if I put an x plus a number inside the parentheses, that shifts it to the left by 2. If I put a number inside the parentheses and subtract it, that shifts it to the right. A number outside the parentheses shifts it up or down, and the plus shifts it up. So this one would be shifted up by 3 and to the left by 1. And you can scale it, so if I had y equals 2x squared, that just means that every point is going to be twice as high as it was before. So rather than 1, 1, it's at 1, 2, and negative 1, 2. So those are parabolas. And the last 2, 3 that I think you need to know, y equals x cubed. Y equals x cubed looks like this. Goes through 0, 0, 1, 1, and negative 1, negative 1. Y equals the square root of x looks like this. And it has the point 0, 0, and 1, 1, and 4, 2. That's supposed to be 4, 2. And 1, 1, and 0, 0. You should also know about the absolute value function. Y equals the absolute value of x. And that's a V-shaped function. So that's y equals absolute value of x. And the same translation sorts of things work. So y equals x minus 3 takes this and translates it 3 to the left. Okay, so now you know everything there is to know. You don't really, but that's the different families of functions. So that's a lot of information there. So now let's go back to this one. Sketch the graph of the function f and find the x values at which f is continuous but not differentiable. So now this is going to be a piece of cake. So we have, for x less than 0, it equals negative x. So less than 0, so I still have to put in 0, so when I plug in 0, I get 0, but I'm going to put an open circle because there's no equal sign there. It's a line, so I need one more point. When I put in negative 1, negative 1 is 1, so I get this line. Between 0 and 1, it's x, and so I'll plug in 0. When I plug in 0, I get 0, but that's an equal sign, so that's a solid dot, so it fills in that open circle. I need one more point. I'll go ahead and put in 1. When I put in 1, it gets me 1, but there's no equal sign, so that's an open circle. And then x greater than 1, it has the value of 2. And remember, 2, that's just a constant, and it does have an equal sign, so I'll have a solid dot, so it'll look like that. So where is it continuous but not differentiable? Okay, so first of all, there's only one place where it's not continuous, and it's not continuous right there, so not continuous there. Every other place it's continuous, because in every other place, the limit from the left equals the limit from the right, and the function equals that. But it is not differentiable at x equals 0, and we can tell that because we have that sharp peak there, that cusp, and you'll learn more about differentiability later, but right now that's what you want to be looking for. So where something is not differentiable is when it has a sharp peak like that or like that will make it not differentiable. If it's not continuous, it's already not differentiable. If it is continuous, it might or might not be differentiable, but if it's not continuous, it is not differentiable. So the answer to this question is at x equals 0, f is continuous because the limit as x approaches 0 of f of x equals 0, and f of 0 equals 0, but it's not differentiable. All right.